How's it going, Tyler?
It's going good, Makoto. How about yourself?
Yeah, not bad.
Not
Decided
bad.
to show up to class, early for once.
Yeah, it's impressive. Just kidding. Yeah.
What are you doing on Friday? I actually wasn't there for the problem session.
We did some problems. So I think Menzelos did a problem.
Yeah.
Which one did he do? He did a couple. He did one with like the cohomological dimension.
Oh, I see.
Yeah, and then Paco did I think 3.2, which was like an explicit cohomology, if I recall. Hello. Yeah, right, Makoto. That's the Fridays aren't recorded, as far as I know, so you don't get to see.
Yeah, so that's why I want to make sure, I'm not going to do any problem that someone's already done. So.
Yeah, I see. What are you doing?
I don't know. I was going to ask first to see which one's free.
That's fair.
Yeah. No, I had an interview on Friday, so I wanted to take time off before class and stuff.
That's fair. How's it going, Freddie?
Going all right. How about the rest of you?
It's going good.
Are you all going to the botanical garden this weekend? Is it this weekend? Yeah, it's this weekend.
Oh, is this the Cam's email?
Yeah, from Como, I think.
I clicked it and I did not read it. Let me check it out.
Yeah.
I think I might, but I'm not actually sure. I think that it's so far away, right?
I mean, it can give you a ride. Like, it's not. I mean, like maybe not us, but like someone can give you a ride for sure, Mendoza. You should totally come. You haven't hang out with us like physically so long.
Yes, I know. I only used to see Andy. I have seen him like twice this semester. And Zach, of course, yes. And Zach, who did it after me. So that's the only place even in the last department this semester.
I see.
Hopefully, the vaccine will be here and we'll get it before the end of the semester, right?
Yeah, that seems pretty dubious, but yeah, who knows?
Dubious? Okay, I didn't catch what was dubious, but that's all right.
Oh, we're just talking about like if you're going to get the vaccine before the end of the semester or not.
Ah, I agree. Seems dubious.
Yeah.
I mean, I might go so far as to say no, but yeah. All right. Any questions? So yeah, let's see. Just trying to move things along as much as can reasonably be done. So today I want to talk about the transfer. So it's easy to give the definition of the transfer as the restriction map in group homology, but then it has a classical group theoretic definition. And so I want to give a result which explains why the homologically defined transfer coincides with the group theoretic transfer. As I said, there's a statement of a result of Furtwängler, a certain result about the triviality of the transfer homomorphism. Again, I'm not gonna prove the proof takes a few pages in Harari's text, and you need it to do some really important result, maybe like the principal ideal theorem or something in global class field theory. But I hope we get to global class field theory. So if we don't get there, we won't need the result. So so we'll definitely going to skip it for now. The proof actually looks quite elementary. It's like some group ring calculations, linear algebra type calculations. So the proof was well done. I mean, maybe if somebody wanted to present something, in a Friday problem session, maybe presenting that would be a way to go. Anyway, so yeah, I'll talk about the transfer, and then I'll talk about the Herbrand quotient, which is a relation, sort of the cohomology of a finite cyclic group, as we already saw, is much simpler. And so the Herbrand quotient is kind of saying a little bit more in this nice simple situation. I like that because it's just not very technical. We can actually go through all the proofs. That should do it for today. I think I could be mistaken, but I think the last main topic in chapter 2 is cup products. And so there's a very long, very detailed discussion of cup products, which I think is good. For now, I may just give the definition, state some of the most important properties. This is what I asked, why do we like cohomology better than homology? And Hayang answered, because we have a product operation in cohomology. And I think that's the right answer. So this is very, very important operation. Yeah, and then I think we'll be off to chapter 3, which is, what is that? Like special things about Tate cohomology of P groups, I think. So there's a Tate-Nakayama lemma. And then I think the next chapter is Galois cohomology. So again, we need to just, like to move things along as much as we can. Okay. Any questions before I start in with it? No? Okay. All right. So yeah, transfer. Great. So if I take I was defining it last time following Harari for a finite group and an arbitrary subgroup, but again, I forgot for a second that Harari basically only works with finite groups. And in fact, you can see from the definition that really you can define the transfer for any finite index subgroup of a group. That's the standard definition, and it is not an isomorphism in general. Homomorphism. So yeah, so this is the restriction map. So again, this is one of these natural maps that, again, we didn't, I sort of bailed out a little bit of giving you the definition. I gave you the restriction map on the level of H0, okay, and then that'll come up. The restriction map on H0 is some kind of relative norm map, just like the co-restriction on cohomological H0 is some kind of relative norm map. And then through through the magic of delta functors, that induces restriction maps in all the other homology groups. But what is that map? And that's what we're going to do. Right. And so let's see. Let's get into this. So quite a while ago, we took the homology of this exact sequence of G modules, and so this was a very general, again, this is just the augmentation map and its kernel, the augmentation ideal, right? And so we took, homology of this, right? I guess the main point is that the homology of ZG was trivial because the homology is, among other things, is a Tor over the group ring ZG, and that's a free ZG module, so it's projective, so it's flat, so it's acyclic for Tor. Anyway, so if that's the only thing that you use, that the ZG is acyclic for group homology, and then you write out a little bit of the homology sequence, and you get that the first group homology is isomorphic to that, the augmentation ideal modulo its square. And then you say, well, actually, from topological considerations, I was expecting the first homology group to be the abelianization of the group itself. And yes, it is also that. And it's just you just much more directly, you just check that, in fact, the map induced by just taking a group element to the group element -1, well, that certainly maps you into the augmentation ideal. And you check, it's not completely obvious. Somehow it looks a little unlikely to be a group homomorphism. There's something multiplicative to additive going on here, but it is. And I went through this quickly, but you literally write, there's the map, and you write down the inverse map, and you check that this is an isomorphism of commutative groups. Okay, and so therefore you can think of the transfer map. Well, since H1GZ is isomorphic to this, is isomorphic to the abelianization of G, therefore a map from H1 of GZ to H1 of HZ is giving you a map from the abelianization of G to the abelianization of its finite index subgroup H. Again, that's the fact that you have a map in the other direction is obvious, and the fact that you have a map in this direction is not obvious and is really using the fact that H has finite index in G. Okay, so I want to so manipulate this definition to get the classical description. Okay, so let's see. The first step is, so I had this sequence and I took the G group homology and I got that. Well, if it's a sequence of G modules, then by restriction, it's also a sequence of H modules. So I could take the H homology as well. Okay, and so I'm writing it down. It certainly looks pretty similar. And then again, the key fact here is that ZG is a free, hence projective, hence flat ZH module. And again, this group homology is some Tor over the ring ZH. So that's 0, 2. Okay, and so, but that we don't get an isomorphism this time. We get an injection from H1 HZ, okay, which again, as we just discussed, is H mod H prime, the abelianization into this guy. Well, that's the 0th homology, so it's the co-invariance of H acting on G. So this should be IG modulo IH IG, because it's the H co-invariance of IG. Okay, and so I just wrote that down. Okay, so yeah, so we have this map, and then right. So what I'm saying is, if you write this map out, then we've identified H1 HZ with H mod H prime, and also with IH modulo IH squared. Okay, and so then once you make that identification, it's easy to, so what could this map be? It's the natural map. There's certainly, from how you can include IH into IG, and does, certainly IH squared is, well, IH times IH is contained in IH times IG. So you get such a map. What was not obvious just by passing to the quotient here is that this homomorphism was injective. If you stop and think about it, what does it mean for the fact that this map to be injective? Well, if you just look at this map, what's the kernel? Well, the kernel is everything in IH that maps to 0 in the quotient. So it's IH intersect IH IG. Okay, and so in order for that map to be an injection, that means that what we might, it's an injection upon modding out by the kernel of this map as a map on IH was that. And so if it's injective upon modding out by IH squared, then therefore IH squared is the kernel of the map. And therefore IH squared is equal to IH intersect IH IG. Oh, okay, something not super fascinating. And then, yeah, and so then I just want a nice little commutative square here. Right. And so, okay, so just tiny little group theory calculation here. So we just decided that H mod H squared is IH mod IH squared. And I just did the calculation that IH squared is IH intersect IH IG. And then you look at this just like, first isomorphism theorem in group theory or whatever, right? So you have a canonical map from from IH into this this quotient map. It's clearly surjective from the image of IH, because it's IH plus some second thing modded out by that second thing. So the map from IH will be surjective, and then the kernel is what it is. Okay, so this is the standard first or second isomorphism theorem from group theory, which is trivial if you just try to figure out what the map is. Okay. So right, and so therefore this map, which was landing in IH mod IH squared, this is also an isomorphism. Wait, is it? Let me do it. Did I? Hold on. Yes. Okay. Right. So well, yeah. Here's the map. So DH was the map that went from H mod H squared to IH mod IH squared, and we just said that IH mod IH squared is equal to that. Okay, great. So just trying to clean things up, and so the idea somehow is that these are isomorphisms. So I'm trying to understand the map up here. This is kind of the more classical one, right? This is actually just the map from the abelianization of G to the abelianization of H. And what's happening downstairs is just somehow like more linearized, right? Here I have like an ideal in a ring modulo its square. And maybe just a little more structure here. So maybe that looks better if you're writing down a homomorphism. So we'll see, in fact, the goal of the next page or so is just to explicitly say what V is and what S is. And it's kind of obvious what S is, just in terms of the way restriction is defined, and then through the interaction through this commutative square, right? That's going to tell us not just the commutative square, but these guys are isomorphisms. So okay, not the. If I'm telling you that it's kind of obvious what this map is and these two vertical maps are isomorphisms, then it's probably not the biggest deal in the world to figure out what this map is. Okay, let's do it. So here, first of all, the slightly technical coset representatives thing. So R, just following Harari's notation, is a set of right coset representatives for H and G containing the identity as one of the representatives. And then it follows from the way coset representatives work that if I take any element of the big group G, I take one of my coset representatives, okay? And now, you know, so rho is like a right coset representative, but now I'm multiplying it on the left by an arbitrary element of G. So, okay, whatever, I get some element of G. What does it mean? So therefore, there must be a unique coset representative, probably a different element of R that I'm calling rho prime, multiplied by another element of H. So, okay, you don't have to love it, but you can't really argue with it. It's just how coset representatives work. Okay, and then this rho prime is suppressing. The rho prime definitely depends on sigma. Okay. So here's the statement, right? And so you can see that what is the S map, which I'm saying is kind of obvious. We'll also sort of address that at the end. The S map attached to, you know, an element of this quotient. What are we really doing? We're really just multiplying by, we're summing over all the elements of a system of right coset representatives for H and G. So that's what the map is. And this really, the point being that like, we're gonna understand, again, we're gonna understand this as basically, this is like an H0. It is not like, this is an H0 in group homology. Right, this is literally H0 of G with coefficients in IG, and this, after passing from isomorphism, was an H0 in the group homology of H, and so we're lucky for us on H0 we have a direct recipe for defining the norm map, which actually is essentially this. Maybe I should flip back and show you what it was. Yeah. So here it is. I have a restriction map. Okay, well, this is defined maybe here. Yeah, maybe when I was here, maybe the group was already finite or something. But again, I don't know that we need it, but it makes sense whenever H has finite index in G. Clearly, I'm just summing over coset representatives, so I want there to be finitely many cosets. And so yeah, this level 0 map gets the notation n prime of G mod H, so it's some relative norm on the covariance. And this was an exercise to make sure that this was well defined and that it has both of these expressions. But you can see that the second definition here, look, I'm saying that the map on the H0 is you take a set of right coset representatives for H and Z, and you sum over that on the left, and you let that be your map. Okay, so that is what we're doing here. Okay, so do you see what I'm saying? I mean, the downstairs map is kind of no problem. The more interesting thing is again, you know, what is the map, you know, in the more purely group theoretic terms. And so the answer there is it's the sum of these slightly weird guys. Okay, so this is where the you know, it's not super fancy, but it's a little bit fiddly, right? So you take your set of coset representatives for every G and G and H and H. You write once again, you write rho sigma as sigma sub rho times rho prime, and so that's this sigma sub rho, which is in H. Okay, so you see that this sigma sub rho is defined in terms of sigma and rho, but in a slightly fiddly way. Okay, and so this is the classical expression for the transfer. Right, so it involves going over coset representatives and doing this thing. All right, so let's. If there are no questions, any questions? No. Okay, so I'm just gonna prove it. All right, so if we just keep our head, it's all fine. There's nothing super exciting happening. So first of all, just let me start with the simplest thing. I have some expression which is manifestly 0 in this quotient ig mod ih mod ig, which I'm going to be working in, right? So it just is, because sigma sub rho, again, is in H. So sigma sub rho minus 1, that's exactly the type of thing that's in the augmentation ideal of H. And this sigma prime is in anything, everything is in G. This thing is in IG, so you must believe me that this expression is in IH times IG. It just is, okay? And so therefore it's 0 in the quotient. Great. What's the point? The point is, if I multiply this out, then I can bring something to the other side. So if I multiply, so 0 is equal to this thing, and if I multiply it out, nothing is happening here. I'm just multiplying it out. And therefore, if I ever see this complicated expression, and I'm working modulo IH times IG, which of course it will be, then I can replace it with this simpler expression. Okay, that's all I'm doing. All right. So now let's see all this. Yeah, so I'm trying to compute the transfer, right? And I'm going to compute the transfer. If I compute the transfer and then I take this isomorphism, well, the diagram commutes, so it goes the other way. So I could compute dg, and then again, this really is just the relative norm map. Okay, so right, and then dg applied to an element is just that element minus 1, so no big deal. And so yeah, after you apply this dh isomorphism to stick you inside this funny quotient, subquotient of the group ring. So the group ring, what the transfer looks like inside the group ring is just this: relative norm map applied to sigma minus relative norm map applied to 1. Okay, so let's do it. I just recopied what I had up there. And now we write out what was this relative norm map. I just showed it to you, right? It's literally, you take your system of right cosets and you multiply on the left and you sum over it. Okay, that's exactly what I did. Applied to sigma and then applied to 1. All right, and then let's see. This is what sigma sub p is by definition. By definition, rho times sigma is sigma sub p, sigma sub rho, right, which is an H, times rho prime, which is a different coset representative, and I didn't do anything there. Okay, and let's see, and so then what's happening? Oh yeah, so the only thing I'm changing here I'm summing over all my coset representatives of rho. Here I'm summing over all my coset representatives of rho prime. And so just the thing that you have to believe is that here we're fixing an element of G. So with G being, that element of G being fixed, which the notation allows us to do, I mean, again, if you may not see it right away, but if you just stop and write down the way coset representatives work, then this map from rho to rho prime is a bijection on the set of coset representatives. Okay. Stop and think about it if you like. So okay, so since as rho runs over all the elements of R, so does rho prime, therefore the sum is equal to the sum. And then we get this complicated thing. And as I said, if you ever have an expression that looks like this, then you can replace it with the simpler expression here. So this guy, it's exactly the situation, right? I mean, literally, so I just got this thing. But this thing minus this thing is equal to 0 in the quotient, which is where I'm working, so I can replace this guy by that guy. Great. Okay, because again, that's where is DH living? DH is living in this guy. Great. I actually think I'm saying, not to brag, I think I'm saying this slightly better than what Harari says. I don't know why, it's just like a little bit. I found it a little bit jumbled, but okay. Anyways, so or not, depending on your taste. But okay, so since dh is just h goes to h minus 1, right? So now I want to invert dh, but I say, yeah, evidently I can, if I have a map which is like going multiplicative to additive and is sending group elements to group elements minus 1, and then the output of that map is a sum of group elements minus 1, ooh, I know. Before I applied dh, I would just have the product. That's what the inverse of the map is. Okay. And yeah, so I mean, okay, I'll stop and dramatically take a sip of my coffee because that's the proof. Okay, so that gives us the definition of the transfer, which, you know, is a little bit weird. Like, why are we summing over, you know, where summing over coset representatives is okay. The thing which is a little bit weird, again, is this maneuver, right? So we're multiplying on the left by our right coset representative, and we're rewriting it in terms of our right coset representative. That's not the weird. I mean, I don't know, like, you ever see double cosets, like that kind of thing happens like all the time, so it's not so crazy. All right, yeah, and so the formula for S is immediate. I mean, I think, in fact, I think, you know, en route to doing this, we computed S, as I said. This S is just the relative, by definition. What is the restriction? On H0, it's this relative norm map, which was exactly summing over the, summing on the left over the right coset representatives. Okay, great, we got it. So yeah, and so whenever you have a finite index subgroup of a group, you have this transfer map. And again, it's a really interesting, it's just a thing in group theory, and it comes up. Another thing, if somebody really wants to, you know, do something different, you know, why don't you look up what the transfer map is used for in group theory? There's actually I found some nice Wikipedia article on like some focal subgroup theorem that combines like transfer and fusion, which is another kind of deep concept in finite group theories. And anyway, it is just a you know, it's a new ingredient in finite group theory. I wanted to you know, perhaps distract you from the fact that I'm just going to state Furtwängler's theorem and not prove it. I wanted to, you know, give you your money's worth. So I'll say one other interpretation of the transfer, which I just found on this cool website, Math Overflow. They added some nice stuff here. And so someone asked, I think it was probably Martin Brandenburg, who's like sharp young guy, like he just wants to do everything categorically, and he's good at it. And so he asked, you know, is there a completely categorical interpretation of the transfer? Something about, you know, in terms of a junction for abelianization or something like that. And the answers were like, no, there's no completely categorical interpretation of the transfer, but people wrote down various nice interpretations. And there's a very, I don't know that I'll ever use this for anything in my life, but it just makes me feel happier about the transfer to say it. I'll give you a topological interpretation of the transfer, okay? So again, we're trying to define a map from the first, same exact, G is any group, H is any finite index subgroup. We're trying to define a transfer map from first homology of G to first homology of H. But again, it's Z coefficients. So that's, you know, that's the best topological situation. So as I mentioned, this is literally the topological homology. So the cellular homology, if you like, of the associated Eilenberg-MacLane CW complex, okay? And so you take, so KG1 is your CW complex that is connected, has fundamental group G, has all higher homotopy groups 0, unique up to homotopy equivalence, as I mentioned. And so, okay, its fundamental group is G, and so therefore, just by covering space theory, it has a certain covering space whose fundamental group is H. Right, that's how covering spaces work. And if you think about the way it works, you know, everything inside the, you know, within the entire tower of covering spaces of the Eilenberg-MacLane space, everything in the tower is the Eilenberg-MacLane space for the corresponding subgroup. Why is that? It's because covering maps induce isomorphisms in all the higher homotopy groups. Okay. So all the covers are the Allenberg-MacLane space for their, for whatever their fundamental group is, and which is the corresponding subgroup. And then, okay, you do this maybe a little bit carefully. So you, relatively well-known fact in algebraic topology, if you have a CW complex downstairs, and then you have any topological, unramified covering map, if you need to say that, covering map in the sense of topology, you can put a particular CW structure on the downstairs guy so that the covering map is cellular. And indeed, the pre-image of every cell downstairs is number of sheets of the cover copies of cells upstairs, and the covering map is literally mapping every upstairs cell homeomorphically down to a downstairs cell. So have you guys seen that? No? Right, I don't know. Say yes or no. This fact that if you have a CW structure on your base and then you have a covering map, you can make the covering map look wonderful with respect to the cell structure. No? Okay, well, you can do it. All right. So so what's happening? What's happening basically is that the deck transformation group is literally faithfully is freely permuting the cells. That's the upshot of this. Okay. Gosh, how do you know that the Euler characteristic multiplies by the degree of the cover if you don't know? Okay. It's true. Anyway, so you take such an interpretation, and now I have, so the fact that H has finite index in G means that the covering map is finite sheeted, okay, right? And so I just said that if I basically take a sufficiently fine CW complex, CW decomposition downstairs, that's the way you think about it. You may need to subdivide your cells a little bit smaller in order to do this. And then you do that, and then you say, okay, for every cell downstairs, I literally, so let's say N is the index. I literally, you have just this, okay, I'm sure you guys have seen this picture though, right? Like your money back if you've never seen this, right? And so this is living inside, this is Y mapping down to X, just the stack of pancakes picture of a covering space. Every covering map is locally a trivial covering map. It just looks like a stack of pancakes. Okay, so all I'm saying is that you can make the stack of pancakes interact with your seed. So this can be a cell. Okay, so if you cellularize correctly, then your finite for every covering map downstairs, you literally just have, if this is an n-sheeted covering, you literally have n homeomorphic cells upstairs. I mean, whatever, they're cells. There are cells of the same dimensions. Of course, they're homeomorphic. But the point is that the induced map is a homomorphism on each one of these cells. Okay. But now I can define a map on the cellular complex, right? For each cell here, I have finitely many cells upstairs. So I can't reverse the map as a map. But what is the cellular complex but formal z-linear combinations of the cells? And so therefore, if I want to map back in the other direction on the complexes, I literally map this cell to the sum of all the other cells. Okay, that's what I do. And you see, I've just written it down. So I get a map on the cellular complexes where, what do? You take a cell downstairs, you look at the number of sheets, different cells upstairs that map down to it, and you say, I want the sum of all those cells. What a great map. You can't argue with that, right? And so that gives you, and then you check that this actually gives you a morphism of cell complexes, or you're so bowled over by how nice it sounds that you don't, but in theory, you should check. And then what's the point? Now I have a morphism of cell complexes, and so what? What does this have to do with the homology?
You get a map on the homology, right?
Yeah, what is the homology of a CW complex other than the homology of the cellular complex? That's exactly what it is, right? So if I have a homomorphism from the complex whose homology is the homology of you know, the downstairs guy to the anyway. So you do this and you get a map on homology. Okay. Yeah. By the, I guess actually I didn't even think of this until just now. It seems like you're getting a map on all of the homology groups that way. That's kind of, I wonder. I'll look that up. That actually might be too good to be true. Let me just stop and ponder that for a second. I don't know. Anyway, so that's the map that anyway. So that they tell me that this is the map that you get. Right. Okay. So I'll think actually. Let me kind of think back on that. So maybe there's something where, you know, when you actually check the well-definedness of it, maybe it only think for a second. I mean, on the other hand, you definitely do have a restriction map on all of them. I think it's probably true. I think you get a map on all the homologies. Okay. Okay. And so that's a nice topological description of the trend. All right, and so here's the theorem that I'm not going to prove right now. If we make it all the way to the principal ideal theorem or whatever in global class field theory, and someone says, "Hey, you never proved von Loesch theorem," we can come back and take a crack at it. Maybe. I think the statement is very easy. So you take a finite group, and then you let H be slightly confusingly the commutator subgroup itself, and so then the transfer map is going from the abelianization of G to the abelianization of the commutator subgroup. And the theorem is that this homomorphism is trivial, okay, no matter what finite group you start with. Okay, and again, this takes a little while. So three pages or so in Harari's book, and like a lot of group ring lemmas. And then the one thing that confused me, he started talking about the co-matrix. I was like, co-matrix? I've only ever met matrices. I don't know, but it means matrix of cofactors. So whatever. Nothing too bad. Okay. Any questions about transfer? Okay, hopefully it'll come up in practice soon. I don't know, that soon, at some point. All right, so now I want to go to Herbrand quotients, which are easy. So good for us. So we take a finite cyclic group. I'll give you a generator, same as we did before. And then what we point out, kind of my motivation for Tate cohomology is that once you fix the H0, the super H0, and the H sub 0, which we renamed as H super minus 1, once you pass to the quotient on the super H0 and pass to a sub guy on the sub H0, then they become the same as all the other ones, and we get a two-periodicity of the Tate cohomology groups of a finite cyclic group. So all the even numbered ones become equal to Tate H0, which is normal H0, the invariance modded out by the image of the norm map. Right? In fact, normal H0 would just be that, and then we just computed that all the higher even cohomology groups were this guy divided by this guy. That was our motivation for correcting the H0, and then similarly, all the odd ones that's correct, are H sub 0, which by definition is H super minus 1. Okay. And so, yeah, so regular H sub 0 would be A mod IG of A. I don't know if we're going back to just calling it I. So the co-invariants are you mod out by the augmentation ideal, as we've discussed. But then, so that would be what the ordinary H0 is, but all the higher ones are not that. They're the kernel of the norm map divided by, modded out by the augmentational ideal. And so so we have this very, very nice two-periodicity. We have an infinite sequence of Tate cohomology groups. They're probably not zero, right? I think this came up in one of the problem sets, right? Neither one of these has to be zero for sure. Okay. Right. And so okay, so we have, and so you see that it's so much simpler we introduced infinitely many take homology groups in both directions, but there's only 2 of them that are different. And so now, we're in an unusually simple situation, and we want to squeeze even harder. We want to just, how simple can we make this? Okay, and so this is the notion of the Herbrand quotient is studying the discrepancy in size between these two different groups. Okay, when they're finite, they don't have to be finite, but there's some things to say about this. Okay, so let's suppose that, I mean, again, by the result, if A was a finitely generated as a Z module, then we proved that it was finite. It might turn out to be finite otherwise. Okay, so if I have a G module, if both of these groups are finite, let's just do little h super 0 of A to be the order of the tate H0, which therefore is the order of all the even number take homology groups. Little h super 1 of A, which is the order of all the odd number take homology groups. And then we define H of A. This gets a fancy name, the Herbrand quotient. This is a positive rational number. It's exactly what it looks like. It's just measuring multiplicative discrepancy between the size of the H0 and the H1, assuming that both are finite. Okay, but it turns out that there's a lot of things you can say about this Herbrand quotient, and then that helps you understand the cohomology. Okay, so here's the theorem, and it's not, we can just prove this theorem. I think I'll spend the rest of the lecture proving this theorem. So G is a finite cyclic group, of course, same as before. So first of all, if I have a short exact sequence of G modules, I'm kind of wondering when these Herbrand quotients are defined. In other words, when all the cohomology groups are finite. So the first assertion is that if any 2 of them have well-defined Herbrand quotients, then so does the third. Okay. And I forgot to write something in. So as part of part A, we should also prove that once all 3 of them are defined, then it turns out that the Herbrand quotient of the middle one is equal to the product of the Herbrand quotients of the things at the end. Because there's like a lot of like relatively short, finite length exact sequences of finite abelian groups and relations on the size imposed by a finite length exact sequence of finite abelian groups. That's basically what's happening here. Okay. The next part of the statement is that if A is literally finite, so of course H0 and H1 are finite, then in fact the Herbrand quotient is trivial. In other words, the H0 and the H1 have the same size. That's useful. Okay. Finally, if you have this map, which from some previous life, I think Sayre studied this type of condition when in his real youth, when he was so young that all he could do was compute homotopy groups of spheres. He studied this type of homomorphism, where a homomorphism of infinite groups, but the kernel and co-kernel were both finite. Okay, so in other words, like this F is like only finitely much away from being an isomorphism in the sense that its kernel and co-kernel are both finite. So if you have a G module map with finite kernel and co-kernel, then that's close enough to make the Herbrand quotient of A equal to the Herbrand quotient of B. Okay, so whatever, this is what it is. It's just, we're just trying to get our hands on the relations between the sizes of the 2 different cohomology groups of the finite cyclic group. Okay. Any questions about the statement before I proceed to the proof? Nope. Okay. All right, let's do it. Okay, so first I just want to recall something. I mean, I don't know. It could be an exercise, but I just feel like it's probably the level of the course is too high for this to be an exercise. I don't know. So if I have a finite exact sequence, an exact sequence, from A0 up to AN, and then it goes to 0, and this is an exact sequence of finite commutative groups, okay? You've probably seen this before, that if you take the alternating product of the sizes of these groups, then you get 1. Yeah, people seen that? Yeah, okay. I mean, there's also if there were like finite dimensional vector spaces, then the alternating sum of the dimensions would be 0. So something similar thing. Anyway, Not at all hard to prove. Okay, and then of course we're going to use this all over the place. All right, well now comes kind of the fun thing. So what is the two periodicity mean of the Tate cohomology? Well, again, we had a short exact sequence and we get a long exact sequence in Tate cohomology, by which I mean it's infinite on both ends. But well, look, if the cohomology is too periodic, it's not really that long. You can think of it as an exact hexagon, right? So it's, track me through it. I start at the 0A, 0A, 0B, 0C, coboundary map 1A, 1B, 1C. Now I should have a coboundary map into H2 G of A, but that's what I said. It's too periodic. Okay, so you can canonically identify the H super 0 with the H super 2. They're both isomorphic to the same thing. And so yeah, so you can view this as being an exact hexagon. Okay. Well, that's cool. So all the exciting stuff, I guess, happens when we join things back up again, right? And so the exactness at this point means, of course, that the kernel of this map alpha is equal to the image of this map beta, of course. And so let's just call J to be that common group, okay? And now we're going to unravel the hex. All right. I want to make like a WandaVision reference, but I can't think of anything funny, so I guess I won't. So we unravel the hex, and yeah, so you just do it, and so you get everything. You unravel it, and then you get the kernel maps into the exact sequence, right? Everything is exact, but if you just start with this sequence here and you say, okay, well, what do I put here? Well, what I put here, of course, is the kernel of alpha. What do I put here? What I put here is the co-kernel of beta, which is okay. So yeah. Did I say this correctly? Let me think for a second. Yes, I did say correct. I didn't. I think I said I shouldn't. I said co-kernel when I shouldn't have, but everything else was correct. Okay. Yeah. So you get this, and then well, what do you think we should do? Well, we should use this. We should use the fact that if you have this type of sequence of if all the groups are finite, then we get this relation on the products. And then what was the first thing we were supposed to prove? We were supposed to prove that if any two of the guys had finite Herbrand quotient, then so do the other ones. Yeah, so first, just maybe kind of insultingly, again, I'll remind you that if I have just the shortest possible exact sequence of Z modules, and if the two guys at the end are finite, then the thing in the middle has to be finite as well, right? So why is that? I mean, whatever, it's so easy, so I can tell you. So suppose by contradiction, suppose that Z were finite and Y were infinite. Well, in that case, Y modulo the kernel is finite and Y is infinite, so the kernel needs to be infinite in order to become finite when you mod out by it. But the kernel was the image of gamma, so the image of gamma is infinite, so certainly X is infinite. Okay. So that's certainly clear. And then you look and you just say, yeah, I can do this. So for the sake of argument, let's suppose that A and B both have finite Herbrand quotient. So that means that these guys are finite, and J is a subguy of this, so J is also finite. And so therefore, this J is also finite. And then you say, okay, this C, which I wasn't saying anything about, is trapped between these two finite guys. Same for this C. Okay, so I just did if A and B are finite Herbrand quotient, then so is C, and there's two more cases to do, and they work the same. Okay, so that explains why if two of them are finite, so is the other. And then I believe if you just, oh, it looks like maybe I forgot to, yeah, I think I forgot to tack on the statement, so I forgot to tack on the proof. But of course, we are getting a relation here. We're getting that the size of this times the size of this times the size of this times the size of this is equal to, the other one. So I have, if I did it correctly, I have 8 terms here, right? And both of them are going to include, this is the first term, this is the 8th term. So 1 times 3 times 5 times 7 is equal to 2 times 4 times 6 times 8. 1 and 8 are going to cancel out. And then if you look at that, whatever that, 3 times 5 times 7 is equal to 2 times 4 times 6 relation is, it's exactly this relation. That H0 of B divided by H0 of A is equal to H0 of A divided by H1 of A times H, whatever. It's this relation. All right. What about part B? So suppose in part B we were assuming that A itself was finite, and so again, Tate cohomology of even a finitely generated module is they're all finite. So if it's finite, so for sure H0 and H1 are finite. And then I just remind you we have a couple of maps here that we've seen before. So this is sigma minus 1, and you look at this and you say, well, what's the kernel of this map? The kernel of this map is everything on which sigma acts as 1, but sigma was the generator, so that's literally the invariants, the things that are trivial. What's the co-kernel of this map? Sigma minus 1 generates the augmentation ideal because it's a finite cyclic group. And so therefore the co-kernel here is, well, the co-kernel of multiplication by the augmentation ideal, A mod I of A, which is, anyway, so both of these things, the exactness of this sequence is literally the definition of this H super 0 and the H sub 0. So that's great. And then you come down the other way and you see that we have a norm map, and in exactly the same way, if you stop and think about this, you'd be like, yes, this is literally the definition of the H lower 1. It's not the entire H upper minus 1 was H lower 0 hat. So the hat means it's not the entire H0, it's the kernel of the norm map. Yes, that's exactly what it is. Similarly over here, the hat is saying, no, you're not getting the entire H super 0, you're getting the co-kernel of the norm map. So again, the exactness of this sequence is really the definition of these two Tate cohomology groups. Okay. Well, great. So what does that show us? Again, we know that the alternating sum is equal to 0. So if I take the alternating sums here, or the alternating products, I guess, right? So that, again, the A's cancel out. And so this one tells us that the size of without the hats, the H super 0 is equal to the size of the H sub 0. And then you do this one, and you use the fact that these guys, that we just learned that these guys have the same size. And then that tells us that these guys have the same size, which is what we wanted to show. Okay, so this works out very nicely. There was a part C, similar. It's nice when things are easy. Right, and so now we have a homomorphism with finite kernel and co-kernel. So okay, just write out make a short exact sequence which shows you the kernel, and make a short exact sequence which shows you the co-kernel. By J is of course just the image. In Harari, he writes I, but it shouldn't I still be reserved for the augmentation ideal? I think so. So anything but I. Okay, and so we have such a thing, and then what's going on? If H of A is, what are we trying to show? We're trying to show that if the Herbrand quotient of A is defined, then the Herbrand quotient of B is defined, and they're equal. So let's just assume that the Herbrand quotient of A is defined and show that. So if the Herbrand quotient of A is defined, and we know that, we don't know that K is finite because the Herbrand quotient is defined. We're assuming that K is finite. That's our hypothesis. And so therefore, though, again, by what we just proved, if K is finite, certainly the Herbrand quotient of K is defined, and moreover, the Herbrand quotient is 1. That was part B that we just proved. So by using everything we just proved, if this one has a defined Herbrand quotient, so does this one, and therefore by part A, J must have a well-defined Herbrand quotient, and also by part A, the Herbrand quotient of part A is the product of these two, but by part B, this one was finite, so its Herbrand quotient was equal to 1, and therefore the Herbrand quotient of A is equal to the Herbrand quotient of J. Wonderful. Now we come over here and say the exact same thing, basically, right? So now we just argued that J had a well-defined Herbrand quotient, and we were given that the co-kernel was finite, so that has a well-defined Herbrand quotient, which is equal to 1. 2 out of 3 is good, and so the Herbrand quotient of B is well-defined and is equal to the product of the Herbrand quotient of J and the Herbrand quotient of this finite thing, which we just proved is equal to 1. So the Herbrand quotient of B is also equal to the Herbrand quotient of J, the image of the map, whatever that was, which is still equal to the Herbrand quotient of A. Okay, we proved it. Yeah, so the cohomology of finite cyclic groups is really pretty nice. Yeah, I mean, it comes up. Yeah, so for instance, like when we're studying local class field theory, the residue field is going to be a finite field, and therefore the absolute Galois group of the residue field is going to be a procyclic group. It's going to be isomorphic to z hat because there's going to be one finite extension of each degree. And so z hat is the inverse limit of finite cyclic groups. And so if we're looking to do Galois cohomology over the residue field, which is reasonable if you're trying to understand a local field, you probably want to understand what's happening over the residue field. And so, yeah, I'm pretty sure that these type of Herbrand quotient calculations are going to come up when we do local class field theory for that reason. Okay, that's all I have. That's a lot of writing, I guess, but most of it went pretty quickly. You can look back at this beautiful stack of pancakes picture. Yeah. So again, so next time I'm going to do cup products. At most one lecture about cup products, and then we, there's going to be a lot more information about cup products, which is good. Yeah. So for instance, like I guess I should say, so when I was your age, roughly, I was reading my class field theory out of Serre's local fields, which is a standard reference. So it's like, part 1, basic local field stuff. Part 2, like higher ramification theory of local fields and like the Artin, Artin character. Part 3, group cohomology and Galois cohomology. Part 4, local class field theory. So that's the way that Serre's book is. So it's still it's not as readable as it could be. It's still a very good reference. And so one thing that I remember is he's kind of like recall the cup product in group cohomology as though you learned it somewhere else, which was definitely not the same. And I think he gives some definition of the cup product that is so abstract and fancy that it's not even clear how to compute it like on the cochain level using his definition, which is like someday you're going to have to compute a cup product using cochains. And so Harari's book it's really nice actually that it has such a substantial discussion of computing cup products. So okay, well that's what we're going to do on Wednesday. So see you then.
See ya.